Welcome to this lecture on transition metal organometallic chemistry from principles to applications. In the last lecture, we have been discussing a very interesting topic on CF activation. Now, carbon fluorine bond being among the strongest, this CF activation is the most challenging of all activation that we have encountered so far. So, CF activation is more challenging than for example, C activation as well as H activation. However, that being said, there are a lot of examples where CF activation has been achieved. In our last class, we have seen how CF activation has been achieved in form of 2 or 3 examples that we have looked into close details. One was about achieving CF activation by addition of an electron to a compound making a radical anion, and then the radical anion decomposing into anion and a radical species, achieving CF activation. In another example, we had seen that CF activation was achieved by coordination to electron deficient transition metal, that also resulted in CF activation. And lastly, we had seen CF activation in a transition metal perfluoroalkyl sigma complex, where when treated with TMS triplet, one CF activation occurred, resulting in the formation of TMS fluoride and transition metal CF2 carbene complex. Now, having seen that several strategies in place for CF activation, despite the fact that it is one of the most challenging activation to perform with respect to the other activations that we have spoken about like CC and CH. In today's lecture, we are going to see this in more details about examples which achieve such CF activation in a very simplified manner. So, here is an example where the CF activation has been achieved in a catalytic fashion. Transition metal complex. This is illustrated in the examples shown over here. Reaction of perfluorobenzene C6H6 with dihydrogen in presence of a base triethylamine as catalyzed by a rhodium complex at 95 degrees centigrade and 6 bar pressure produces the CF activated product in terms of giving C6F5H along with triethyl NH plus and F minus. To note that these one of the CF bond of perfluorobenzene has been cleaved, and to it hydrogen activation has occurred and a hydrogen gets attached to it, giving to this CF activated product C6F5H and protonated base fluoride, which is triethyl NH plus. What is remarkable about this transformation is that not only the CF, a very challenging CF activation has been achieved, but also this has been achieved in a catalytic fashion by this rhodium catalyst, also at not too harsh a condition, 95° centigrade. So, this is rather considered a very mild condition for achieving CF activation, because of the fact that CF bonds are extremely strong. So, what we are going to do is we are going to now look at how this reaction proceeds in terms of the mechanistic cycle it undertakes to carry out this CF activation. The catalyst, which is L4 rhodium hydride, is, one can say, both coordinatively saturated, because it has a coordination number of 5, and electronically saturated because it is a 18 valence electron compound. The oxygen state of rhodium is rhodium 1. So, that being the case, this may be considered as being catalytically inactive. So, this precatalyst enters the catalytic cycle by elimination of one of the L ligands, giving rise to L3 rhodium hydride complex. Here too the rhodium is in +1 oxidation state, and it has now become electronically unsaturated as a result of the loss of these L ligands, and currently it is a 16 valence electron complex. And also the complex has undergone a loss in its coordination number. This complex, which enters the catalytic cycle, reacts with perfluorobenzene C6F6 and the base, which is triethylamine, to give the CF activated product in terms of base getting protonated from this hydrogen and the CF getting cleaved because of the activation, giving a fluoride anion, and the C6H5 bond then get attached to the rhodium complex. So, this is a CF activation step where the fluorine gets cleaved and ends up in the anion, and the remaining C6F5 binds to rhodium, and this proton is gets protonated on the base. This itself is also a rhodium 1 compound, and it is a 16 valence electron complex. So, now that CF splitting has happened, the second reagent, which is the dihydrogen, reacts with this L3 rhodium perfluorobenzyl complex, giving this rhodium dihydride complex. This is an oxidative addition step in which dihydrogen molecule oxidatively adds on the low valent rhodium 1 L3R C6H5 complex, giving rise to this 6 coordinated rhodium dihydrogen complex as shown below. So, here we see dihydrogen adding on to rhodium, giving rhodium dihydride, and the 3 L ligands are occupied the coordinate site, and the sixth one being occupied by this C6F5 ligand. So, here the rhodium is in +3 oxidation state, and this also has become an 18 valence electron complex after the oxidative addition of the dihydrogen has occurred. So, this step is an oxidative addition step. The next step which follows this oxidative addition step is a crucial step that eliminates the hydrogenated perfluorobenzene, which is C6F5H, and as one can see that this release is because of reductive elimination between this C6F5 and the rhodium hydrogen bond. So, After this oxidative addition, the next step which follows is reductive elimination. Giving rise to the rhodium 1 L3 rhodium hydride complex. This complex, in presence of this L, can give back the pre-catalyst. So, what is demonstrated over here is a very efficient catalytic cycle for CF activation using a rhodium complex. So, we have seen that important and difficult as the one like CF activation can be achieved not only in a stoichiometric fashion using stoichiometric reagent, but also can be achieved using catalytic fashion the way by this rhodium complex as has been shown over here. So, this is a nice demonstration of catalytic cycle that carries out CF activation efficiently. So, with this we sort of finish our discussion on perfluoroalkene complexes. Now, to give a brief overview as to how we have been discussing these transition metal sigma alkyl complexes, we have seen that we started off with alkyl type complexes, and in transition metal sigma alkyl complexes we have covered CH activation, as well as CC activation, we have also seen how these activations occurred. Now, after considering transition metal sigma alkyl complexes, we have then looked into this very important transition metal sigma perfluoroalkyl complexes. These are represented by Tm sigma Rf, and in this context we have looked at CF activation reactions, now these are a class of compounds which has a commonality, the commonality being that these are transition metal C carbon sp3 type complexes that we have looked into. Now, we are going to go beyond these sp3 type complexes and look into some examples of transition metal C sp2 types in the course of next lectures. And to begin with, we will look at some of these ligands. Now, in our earlier discussion on type of transition metal sigma alkyl complexes, we had shown that sigma alkyl complexes can be of carbon moiety which is of CsP3 types, can also be of carbon moiety which is of CsP2 type, and can also be of carbon moiety which is of Sp type. So, along this, now we are going to take a look at two such examples of transition metal complexes. One is transition metal sigma alkenyl complexes. These can be represented as where this carbon is CsP2. We are going to also look at transition metal aryl complexes. And these are given by MsP2 type. So, this is the sp2 center. So, these would be the type of compounds that we would be discussing now for transition metal CsP2 type. And as for the transition metal Sp type, we are going to talk about transition metal alkynyl complexes, and these are called alkenyl complexes, where this carbon is CsP. So, over the last few lectures we have covered up to this part, and now we are going to go and look into these two kind of systems. As far as these ligands are concerned, this alkenyl, aryl, alkynyl, these ligands occupy an intermediate position between sigma donor alkyl ligands and sigma donor pi acceptor carbon monoxide PR3 and RNC ligands. Now, this is a very important statement as far as these ligands are concerned. So, in terms of their bonding with the transition metal, they thus occupy a position which is between completely sigma donor ligands as well as sigma donor pi acceptor ligands. So, that what does that indicate is that this ligand has intermediate ability to behave as a pi acceptor ligands. They are not too strong as a pi acceptor sigma donor, but also they are not fully a sigma donor system. We are going to look at these in bit more details. Now, let me summarize what has been covered in this lecture. In this lecture, we have looked into CF bond activation reactions, and particularly we have looked into a very nice example of a transition metal catalyzed CF bond activation reaction using molecular hydrogen under not too harsh conditions, rather mild conditions of 95 degree centigrade and 6 bar of hydrogen pressure in presence of a rhodium catalyst that could activate a CF bond of the perfluorobenzene and replace that with molecular hydrogen to give C6F5H under catalytic fashion. We have also looked at the various type of CF activation reactions and the examples of it, and with that we concluded our discussions on transition metal sigma alkyl perfluoroalkyl complexes, and we have also discussed the next set of compounds that we are going to be taking up, which are transition metal alkynyl and alkanyl transition metal aryl complexes, which has transition metal bonded to carbon of CsP2 hybridization as well as CsP type hybridization. So, with this I would like to conclude today's lecture, and in next lecture we are going to take up transition metal CsP2 as well as transition metal CsP type compounds, look at their properties, synthesis and the reactivity in much more detail and compare the same with that of the transition metal CsP 3 types compounds that we have covered so far. In the transition metal CsP 3 type compounds, we have looked into transition metal sigma alkyl and transition metal sigma perfluoroalkyl complexes. So, till then, goodbye and see you in the next lecture. Thank you.